In episode 99, titled Boosting, Gradient Boosting, and Why XGBoost Often Wins, we focus on a modeling strategy that feels almost like a disciplined training montage. You start with a weak model, identify what it gets wrong, then add another model to correct those mistakes, repeating until the overall system becomes strong. Boosting is popular because it can achieve high accuracy on structured tabular data, often outperforming simpler approaches when the signal is complex and interactions matter. The trade is that boosting asks more of you because it introduces more tuning levers, more opportunities to overfit, and more complexity in explanation and deployment. At an exam level, you do not need to memorize implementation details of specific libraries, but you should understand the sequential correction idea and why it can produce strong results. You should also understand why often wins does not mean always wins, because the cost of that performance includes governance, compute, and operational discipline. This episode builds the conceptual model so you can reason about boosting as stepwise improvement rather than as a brand name. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Boosting can be defined as a method that builds an ensemble sequentially by adding models that focus on correcting the errors of the models that came before. Instead of training many independent models and averaging them, boosting trains a first learner, evaluates its errors, then trains the next learner to reduce those errors, and so on. Each new learner is added to the ensemble in a weighted way, so the combined prediction is improved step by step. The key is that the learners are not independent, because each one is trained with awareness of what the current ensemble is getting wrong. This sequential dependence is what gives boosting its power, because it systematically targets the remaining weaknesses rather than producing more of the same perspective. It also explains why boosting can reduce bias, because the ensemble can gradually fit complex structure that a single weak learner cannot represent. Understanding boosting as learn from mistakes is the mental anchor that makes the whole method coherent. Gradient boosting is a specific form of boosting that frames the process as optimization of a loss function using additive weak learners. The idea is that you choose a loss function that measures how wrong the current ensemble is, such as a squared error style loss for regression or a logistic style loss for classification. You then add a new weak learner that points in the direction that most reduces that loss, analogous to taking a gradient step in function space. Each weak learner is often a small decision tree, sometimes called a shallow tree or a weak tree, because it is intentionally limited so it captures a simple pattern rather than trying to solve the entire problem alone. By repeatedly adding these learners, the ensemble becomes a sum of many small corrections, each one nudging predictions toward lower loss. This is why gradient boosting can be seen as an iterative fitting process, where the model improves by making many modest adjustments rather than one large leap. At an exam level, the key is that gradient boosting is sequential, additive, and loss-driven. Boosted trees are especially strong at capturing complex patterns and interactions because each new tree can focus on the residual structure left unexplained by the current ensemble. A single shallow tree might capture a dominant split pattern, but it will miss nuanced conditions and interactions that depend on combinations of features. The next tree can then specialize in those missed regions, and the next can specialize further, gradually building a rich representation of the decision surface. This layered correction is why boosted trees often perform exceptionally well on tabular data where signals are nonlinear and interactions matter, such as risk scoring, fraud detection, and operational performance modeling. The model can create different correction rules in different regions of the feature space, effectively stacking many local adjustments into a global predictor. The trade is that this richness can become difficult to interpret directly because the final prediction is the sum of many trees rather than the output of one comprehensible rule set. Still, in terms of pure pattern capture, boosted trees are among the strongest general-purpose tools for structured data. You typically choose boosting when the accuracy gains justify additional tuning effort and added complexity in deployment and governance. If a simpler model already meets requirements, boosting may be unnecessary, especially if interpretability or latency is critical. Boosting becomes attractive when the decision impact is meaningful and the cost of errors is high enough that incremental predictive improvements matter. In many real settings, a small improvement in recall at the same precision or a small reduction in regression error can translate into significant operational value. Boosting is often the tool that delivers that improvement, but it demands careful evaluation to ensure the gain is real and not simply an artifact of overfitting or leakage. The exam expects you to weigh the trade, meaning higher performance potential against increased tuning and governance burden. Choosing boosting is therefore a deliberate investment decision, not a default habit. Overfitting risk is a central concern in boosting because sequential correction can continue until the model starts fitting noise, especially when you add too many trees or allow trees to be too deep. As the ensemble grows, it can represent increasingly fine-grained patterns, and without constraints, it may start to chase idiosyncrasies of the training sample. This often shows up as training performance improving steadily while validation performance plateaus and then degrades, which is the classic sign that the model has moved from learning signal to memorizing noise. Depth is a key factor because deeper trees can capture more complex interactions in one step, increasing the risk that each addition overfits. The number of estimators, meaning the number of trees, also matters because each tree adds flexibility, and too many can produce a highly tailored fit. Recognizing this risk is essential because boosting strength and its overfitting hazard come from the same mechanism of incremental refinement. The primary tuning levers in boosting are learning rate, depth, and number of estimators, and understanding their roles is more important than memorizing any specific recommended values. Learning rate controls how much each new tree contributes to the ensemble, with smaller learning rates making each step more conservative. A smaller learning rate often requires more trees to reach the same overall fit, but it can improve generalization because the model learns gradually rather than making aggressive corrections. Depth controls how complex each tree is, affecting whether each step captures simple or elaborate patterns. The number of estimators controls how many correction steps you take, which determines the overall capacity of the ensemble. These levers interact because a low learning rate combined with many shallow trees can be more stable than a high learning rate with fewer deep trees. The exam-level skill is recognizing these as the main knobs and understanding their conceptual effects on bias, variance, and overfitting. Early stopping is a conceptually simple but powerful control because it halts training when validation performance stops improving, preventing the ensemble from continuing into the overfitting regime. Because boosting adds trees sequentially, you can evaluate the model after each addition and watch whether the validation metric improves or begins to plateau. When improvement stalls for a sustained number of steps, you stop and keep the best performing ensemble rather than adding more trees just because you can. Early stopping turns training into a self-regulated process that uses validation evidence to decide how much complexity is justified. It is especially useful when tuning because it reduces wasted compute on models that would overfit, and it helps you choose the effective number of estimators. The discipline is that early stopping must be based on a proper validation scheme, not on a test set you intend to reserve for final evaluation. When used correctly, early stopping aligns with the core idea of preventing stepwise improvement from turning into stepwise memorization. Handling missing values and monotonic constraints can matter in boosted tree implementations because these features influence both model behavior and governance expectations. Some implementations can handle missing values directly by learning default split directions, allowing the model to treat missingness as informative rather than forcing imputation. This can be valuable when missingness is itself a signal, but it must be managed carefully to avoid leakage if missingness reflects post-outcome processes. Monotonic constraints allow you to enforce that predictions move in a consistent direction as a feature increases, which can be important for policy consistency and stakeholder trust. For example, you might require that predicted risk does not decrease as a known risk factor increases, aligning the model with domain logic and governance expectations. These capabilities can make boosted models more practical in regulated settings, but they also add configuration complexity and require documentation. The exam-level takeaway is recognizing that boosted tree systems often provide practical controls for missingness and monotonic behavior when relevant. Comparing boosting to random forests helps clarify why these ensembles behave differently, because the two methods attack different weaknesses. Random forests reduce variance by averaging many diverse trees trained independently, which stabilizes a high-variance learner like a deep decision tree. Boosting reduces bias by sequentially adding learners that correct residual errors, gradually fitting a more accurate function. In practice, this means forests often provide strong performance with minimal tuning and high stability, while boosting can achieve higher peak accuracy but is more sensitive to hyperparameters and overfitting. This is not a strict rule, but it is a useful conceptual distinction that explains why boosting often wins in competitive benchmarks on tabular data when tuned properly. The cost is that boosting requires more discipline in evaluation and more care in selecting tuning knobs. When you can explain the difference as variance reduction versus bias reduction, you demonstrate exam-ready understanding rather than just tool familiarity. Communicating boosted models requires care because explanations are rarely as straightforward as a single tree path, and explanation methods must be treated as approximations with limits. A boosted model is an additive sum of many trees, so a single prediction reflects contributions from many small rule sets. Stakeholders may ask for a clear reason for a decision, and you may need post hoc explanation methods to summarize feature influence or local contributions. These methods can be useful, but they are not the same as reading a single rule path, and they can be unstable if features are correlated or if the model is highly complex. Communicating responsibly means framing explanations as descriptive of the model's behavior rather than as causal truth, and acknowledging uncertainty and approximation limits. It also means documenting what explanation method is used and ensuring it remains consistent across model versions. The practical point is that boosting can be governed, but it requires more explanation discipline than simpler models. Inference cost must be planned because boosted models can be heavier than forests in some deployments, particularly when they use many trees or when trees are deeper than in a typical forest. Each prediction requires traversing all trees in the ensemble and summing their contributions, which can add latency under high throughput conditions. Memory and compute costs also matter when the model must run on constrained devices or inside strict service budgets. This does not mean boosting is always too slow, but it does mean you must align the model size with the operational constraints of the environment. Early stopping, depth limits, and careful tuning can help manage inference cost by keeping the ensemble compact. The exam wants you to remember that model selection is not just about accuracy, but about deployment feasibility as well. A model that cannot meet latency requirements is not a usable model, no matter how strong its score looks offline. The anchor memory for episode 99 is that boosting learns from mistakes, stepwise improving overall fit. Each new learner is a correction that targets what the current ensemble still gets wrong, and the final model is the sum of those corrections. This stepwise learning is why boosting can capture complex patterns, why it can reduce bias, and why it can overfit if you keep adding corrections after you have exhausted true signal. The anchor also explains why tuning levers matter, because they control how big each correction is and how many corrections you allow. If you keep this mental model clear, you can reason about boosting behavior without getting trapped in implementation details. It turns boosting into a coherent narrative rather than a collection of knobs. To conclude episode 99, titled Boosting, Gradient Boosting and Why XGBoost Often Wins, choose a case where boosting is justified and name its key risk so your answer remains balanced. A strong case is a tabular fraud detection problem with nonlinear interactions and heterogeneous signals, where small accuracy improvements translate into significant risk reduction and where you can afford careful tuning and validation. Boosting is justified because sequential error correction can capture nuanced patterns that simpler models and bagged ensembles may miss, improving detection at a given alert budget. The key risk is overfitting, especially if you use too many trees or too much depth, because the model can memorize noise and produce inflated validation results if tuning is undisciplined. Managing that risk requires careful control of learning rate, depth, and number of estimators, along with early stopping guided by a proper validation scheme. If you can state the use case and the overfitting risk together, you demonstrate you understand both why boosting can win and what it demands in return. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.